Hello friends, we'll take a few more exercises from exercise 2.2 of methods of real analysis by R.R. Goldberg. So take the example for each of following sequence. For each of following sequence, prove that the sequence has limit or has no limit. Prove that sequence has a limit or not limit. Prove that means you have to use epsilon n naught definition for existence of limit or existence of limit. So in that we'll take first to be so n square upon n plus 5. N square upon n plus 5, n plus 1. Okay, as 5 is given here. So here you have to use definition, but you observe here. Okay, so here n square upon n plus 5 is greater or equal n for every n greater or equal 5. Is it clear? Sorry. N square upon n plus 5 is greater or equal n square upon 2n for every n greater or equal 5. Is it clear? And this n square upon 2n is greater or equal n by 2. N get cancelled, is greater or equal 5. For every n greater or equal 5. And n by 2 approaches towards infinity. N by 2 approaches towards infinity means this sequence must have no limit. Sequence has no limit. Is it clear? So suppose limit n tends to infinity of Sn is equal to L. This is my Sn. Then for epsilon is equal to 1 greater than 0, there exists positive integer n naught such that mod of Sn minus L is less than 1. But what is this? Mod of n square upon n plus 5 minus L is less than 1 for every n greater or equal n naught. For every n greater or equal n naught. What this implies is, therefore, L minus 1 is less than n square upon n plus 5 is less than what will get L plus 1 for every n greater or equal n naught. Now your n square upon n plus 5 n plus m for n greater than 5, it is always less than n square upon n plus 5. Okay, so from 1 and 2, from 1 and 2, n upon 2 is less than n square upon n plus 5 is less than, this will become n square plus 5n, and this is 2 times n square. It is 2 times n square. N by 2 is smaller than n by 2 is it right? N plus m. This is smaller denominator than n greater or equal 5. So that is correct. So n by 2 is less than equal to n square upon n plus 5 is less than l plus 1 for every n greater equal 5, or every n greater equal 5. What this implies is, this implies is n is less than 2 times l plus 1 for every n greater equal 5 here, and therefore n is bounded above set. This is contradiction to, this is contradiction to set of natural number is not bounded above, is not bounded above, and therefore our assumption is wrong. Our assumption is wrong. Therefore, limit n tends to infinity of n square upon n plus 5 doesn't exist. If I assume that some limit exists, then we are getting this, right? So n minus 1 is less than this, but now n upon 2, that is n square plus 5n, is less than 2 times n square, means n square plus n square plus n, right? N square plus 5n is less equal 2 times n square plus n square. So for n less equal 5, 5 times n must be less equal n square. 5 times n must be less equal n square. So this is correct. Is it right? Now here you can observe it goes to infinity. Okay. By epsilon n naught definition. By epsilon n naught definition. Now here you can observe it approaches towards infinity. It is not asked. Okay. Additionally, we show n square upon n plus 5 tends to infinity as n tends to infinity. So for this, n square upon n plus 5 is greater equal, just now we have proved it is greater equal n by 2 for every n greater equal 5. Okay, from 1 we have proved this. Now for m greater than 0, for m greater equal 5, there exists positive integer n naught greater than m and 5, maximum of m5, such that Sn is equal to n square upon n plus 5. What will take this? N naught is greater than maximum of m and 5 is greater equal n by 2, and this n by 2 is greater than n naught by 2. Okay, is greater than m, is greater than m. If I take n naught is greater than, 2 times this, okay, for any n greater equal n naught, and therefore Sn tends to infinity as n tends to infinity, is it right? So in our example, this is not asked, but I am observing this approaches towards infinity, therefore this must go to infinity. Now take next example. 3n upon n plus 7 n raised to half. N is equal to 1 to infinity. So here Sn is equal to 3n upon n plus 7 n raised to half. If I take n outside from denominator, we'll get 1 plus 7 upon n is taken outside. As n goes to infinity, this n raised to half goes to infinity, 7 upon infinity 0. So this approaches towards 3 as n tends to infinity. So this is my L. 3 is equal to L. Okay. Now mod of Sn minus 3 is equal to mod of 3n upon n plus 7 n raised to half minus 3 is equal to 3n minus 21 times n raised to half upon n plus 7 n raised to half. This 3n get cancelled, so which is nothing but 21 n raised to half upon n plus 7 n raised to half. This is less equal 21 upon n raised to half. 21 upon n raised to half. Is it right? Or I can take 7 n raised to half, because this n is greater than that. No. N raised to half. 21 n raised to half upon just n. Right? Which is equal to 21 upon n raised to half. Since 7 n raised to half is greater than 0. So this is additional quantity here. So we'll get this is less than this. And this is less than equal to 21 upon n naught raised to half, or any n greater equal n naught. This is 1. Now for epsilon greater than 0, 21 upon n naught raised to half is less than epsilon if and only if n naught raised to half is greater than 21 upon epsilon. If and only if n naught is greater than, if I take square, 21 upon epsilon square. 21 upon epsilon square. Is it clear? So from this, for given epsilon greater than 0, there exists positive integer, n naught greater than 21 upon epsilon raised to half, such that mod of 3n upon n plus 7n raised to half minus 3 is less than epsilon for any n greater equal n naught. And therefore, limit n tends to infinity of 3n upon n plus 7n raised to half is equal to 3 by epsilon n naught definition. Note, by operations or by algebra of convergent sequences, limit n tends to infinity of 3n upon n plus 7n raised to half, this is equal to limit n tends to infinity of, I will take n outside from denominator will get n in bracket 1 plus 7 upon n raised to half, right? Then this n get cancelled. This is equal to 3 upon 1 plus 0, since limit n tends to infinity of 1 upon root n raised to half. This is 0. This is 0, which is equal to 3. Which is equal to 3. So this is by using algebra of convergent sequences. And to judge the limit of sequence, we are using 8. We are using 8. Next example, show that by definition, show that n minus 1 by n doesn't have limit. Doesn't have limit. We'll solve this example. Okay. So suppose limit n tends to infinity of n minus 1 by n is equal to L. If I assume this limit is L, then for epsilon is equal to 1 greater than 0, mod of n minus 1 minus n by minus L is less than 1. Is less than 1. But if I simplify this, what will get? Therefore, n square minus 1 upon n minus L is less than 1. And therefore, L minus 1 is less than n square minus 1 upon n is less than L plus 1. Okay, for every n greater or equal, there exists positive integer n naught, n greater or equal n naught. We'll get this. So this is 1. Now you can observe. Now root n is less equal n square minus 1 upon n for every n greater or equal 2. Root n is less equal this. Okay. And therefore, from 1 and 2, we'll get root n is less than L plus 1 for every n greater or equal to, which implies n is less than L plus 1 its square for every n greater or equal to. This is contradiction to n is not bounded out. This is contradiction to n is not bounded above. And therefore, limit n tends to infinity of Sn means what is your Sn? N minus 1 by n doesn't exist. Again, while showing this approaches towards infinity, instead of this comparing this with m, I will compare root n with m. And depending on that m, I will find n naught greater than m square. For every n greater or equal n naught, root n is less equal to n naught. Is it right? So, depending on that, we will find for m greater than 0, there is positive integer n naught such that Sn is greater than m. Means we will show firstly root n goes to infinity. Therefore, this must goes to infinity. Is it right? By using sequence, definition of sequence diverging to infinity. Sequence diverging to infinity. So try to solve this example by using that definition diverging to infinity. So with this discussion, I like to stop this session here. There are so many examples in exercises. Try to solve that examples. If you have any difficulty, you can ask that in comment box. So thanks for listening my lecture. Bye bye.